Okay, good morning everybody and Happy New Year. Welcome to the first lecture in the new year. So last time, this is where we stopped. Basically we saw how we do the quantization and how we do the conversion to bits. Right? So using code words, and we saw the zigzag scan to get the order for the bits, where we basically can choose a certain quality value and then stop transmitting the less important bits. So here we can see the main JPEG processing step or steps. So in the encoder we see the first step is we do the color transform. Right? We transform what comes from the camera, the RGB, to our YCRCD components. Then we do the subsampling of the color components, for instance using 4-2-0 scheme, and then we apply the two-dimensional DCT to each of those components individually. Yeah, and after that we do the quantization using the quantization matrix that we saw from the JPEG standard. So depending on the quality level, we have different quantization matrices. Then you do the conversion of the indices from the quantization steps to the bits. Right? We turn the indices into code words, into bits, and then we can basically transmit them over our channel. So I guess it should be indices. So and the decoder then is just the reverse steps. So we start with receive bits, turn them back into indices. So I guess it should be the same here. Then we turn the indices back into values, the reconstructed values, which are not exactly identical to the original, since they contain the quantization error. Then we apply the inverse two-dimensional DCT based on the 8x8 pixel block size to the three components. Then we do the upsampling back to the original size and convert it back to RGB, and that means then we can display it on our screen or display, which usually wants to have RGB. And here you also see a reference, this book by Reimer's DVB, Digital Television Technology by Springer. Yeah. So also some tips for debugging when you do programming for the seminar and the assignments. So it helps to divide a program into small functional units, for instance functions, which we can then test individually, independent of other functions. So make small functions which are easy to test, where you know input-output relationships and see if the function is doing what you want it to do. Also what I found very helpful is to use print commands, starting from the front, where it should be correct, and also from the back. Hopefully you know what it should be, and where it might be buggy, and then see where the error might be. So if you have a faulty output and the correct input, then basically you go from the back and from the end and see until and try to find the place where it changes from correct to faulty. And this is the place where you found your bug. Yeah, so basically circling in the bug. So this is usually helpful for debugging, and as I usually say, debugging is the most time you spend for programming. Okay, so that brings us to the next set of slides, number 8. So now we saw how to obtain the bits. But how do we transmit them? Right? How do we get them from A to B? If you have it on your computer, then it's maybe no problem. You store it in the file and you retrieve it from the file and then you're done. But for instance, if you want to transmit it over a wireless channel, it's not so easy. Right? For that you have to think about how to get your bits from transmitter to receiver. And for that we need modulation. Right? So that's the topic here. So here we have the transmitter side, we have the video information, and we usually have some carrier frequency, that's the frequency on which this transmitter transmits. Then we have the modulation, and the modulation here is what actually transfers the information that we want to transmit to the transmitter. Right. So here this transmitter then transmits on its frequency, for instance, some channel, for instance channel number 21, 480 megahertz, or 480 million oscillations per second, and that goes to the antenna of the transmitter. Right? So this might be a transmitter which is located, I don't know, for instance in Erfurt, transmits on this frequency, and then we can receive it here in Ilmenau and demodulate the information that is transmitted. Yeah, and this modulation is needed to transport the information on the carrier frequency. Right. So why modulation? When you look at a typical video signal, for instance an analog video signal like PAL, that has frequencies from 0 up to 5 megahertz. And even if you look at the highest frequency, we get a wavelength of 60 meter, and that would lead to an antenna size of 15 to 60 meter, so not very practical. Yeah, so how do we transmit an image to the receiver? Here we have the receiver, here we have a filter, which filters out the desired program or the desired channel, and then we have demodulation to extract the transmitted information from it. So here, this filter is important for the selection of the program or the carrier. Yeah, so the filters in our receiver are usually still analog, especially at high frequencies. For instance, when we think about satellite transmission, we have 10 gigahertz carrier wave, or the example we just saw, the 480 megahertz. So for these frequencies, it's still much cheaper to use analog electronics. So those filters are analog, and they're used to suppress adjacent channels or transmitters. Yeah, and analog filters which are adjustable, so that we can actually change from one program to another, are technically difficult to implement. So that's why we need a technical trick to solve this problem with fixed filters. So analog filters can be easily implemented with fixed filters. For instance, we can have a quartz, and this quartz is cut according to a certain given frequency, but then we cannot change it anymore. Right? So we have good analog filters, very narrow band, but they are fixed. So that means we would only be able to receive one channel. Right? So this is actually a problem that can be solved with with changing quartzes. So actually, in like 50 years ago, you could get transmitters and receivers which had exchangeable quartzes. For each channel you had a quartz, and you had to buy a new quartz for a new channel. Right? So that's actually a solution, but we can do better. We don't want to buy new quartz for each program that we want to receive. So that's why we use the mixer principle, or the principle of superposition. So here we have a receiver. here we have the receive antenna on the left-hand side, and here we have a band filter which basically filters out a certain band, for instance UHF. Right? So it's kind of a coarse filter. And then in the next step here we have the so-called mixer, which is basically a multiplier which takes the received frequencies of this band, for instance UHF, and mixes it with a certain frequency from an oscillator. Right? This is called a local oscillator because it's implemented locally. And it is adjustable, for instance in fixed frequency intervals for selecting the station. Right? So now we have a fixed filter after this mixing process. So this is our very sharp filter, which can separate neighboring stations. So this is, for instance, usually a quartz filter. So this is made for a given frequency, cut in for a certain frequency, and it's not changeable. Right? For instance, at I think 35 megahertz or something, this might be. So this works to pass a fixed frequency range. But since we have a local oscillator that is variable, which we can change, we can obtain program selection using a change of frequency here. Yeah, so this is actually standardized. So here for this fixed filter, we have a pass band for TV at 38 megahertz. If we have FM, then it's 10.7 megahertz, and for shortwave, medium wave, and long wave, we have 455 kilohertz. So they are standardized because then they can be produced in masses, which makes them cheaper. Right? So you just buy one of those cheap fixed filters. They are quite good in narrow band, but you have to use this mixing in order to be able to apply it to different channels. So what does this mixing do? So in here, this multiplication, still have to see what it does. Now first, how is the frequency generated? This is an example of an oscillator. This might be a typical example for a radio or a TV receiver, or also a satellite receiver. So here you can see you have a transistor, which is a little amplifier, and here you can see the signal is taken from the emitter of the transistor, which means it's non-inverted. So you have the same phase at the output as the input. And if you have an amplifier and you have some feedback, and here you can see you have some feedback, a certain portion of the output is fed back to the input. And if you have no phase, you get an oscillator, if you have no phase lag. Right? And the oscillation frequency is given by this LC combination. Here you can see an L, a coil, an inductor, and here you have 3 capacitors. So this is a structure which can oscillate, like a pendulum. Right? Do you all recognize this? So here basically you have a circuit which can oscillate, and it is excited by this feedback from this amplifier. So this circuit here would still oscillate without this amplifier, but it would only give you a few periods of the oscillation, and then it would die out because of energy losses. Right? There's always losses because you have these wires have ohms, have resistance, and resistance means you dissipate energy. So that's why you need an amplifier to compensate for the losses here. And if you do it, then you have a continuous oscillation. And this is what you need. And in modern receiver, this LC circuit is replaced by a digital control. So actually this circuit is still there, but you have a digital control where you have variable capacitors, which are controlled by voltages, and they are put in a control loop, an additional control loop, and these are called PLL, phase-locked loop. Have you heard about phase-locked loops before? PLL? So basically you have another block which measures the frequency which comes out and compares it with a quartz frequency after dividing this frequency by a certain number. And then it can detect if this oscillator is on the right frequency. And if it's slightly changing, then it fixes the frequency using one of those capacitors. You can use capacitance diodes, which change capacitance according to the voltage applied. And that means you can build a control loop. Right? Fix the frequency according to the comparison to a fixed quartz oscillator. And usually quartz oscillators are very precise. Right? So you not only have quartz filters, you also have a quartz to control the frequency of this variable oscillator. And these PLLs are usually made such that the frequencies that you can obtain are right on the channels that you want to receive. So usually in the TV sets you have the exact channel spacing from one program to the other, so that it doesn't check all frequencies but only the frequencies where there is supposed to be a station, the channels. Right. Yeah, this simple electronic circuit is called a clap oscillator. So this is a very common form of an oscillator. There are different oscillators, but this is actually quite practical and easy to implement. So you can actually build it yourself. It just takes a few components and it's usually quite reliable. So for instance, here you could use a 9-volt battery and those values here, and then it actually oscillates. I forgot what frequency, but it oscillates. Makes sense? So this shows you how to build an oscillator. And when you have high frequencies, you actually do use those analog oscillators. An alternative is to use a digitally produced sine wave. Right? But a digitally produced sine wave goes up to maybe few hundred megahertz, and that's not quite practical for satellite reception or the UHF bands of TVs. But that's
capacitors here are used for filtering the circuit. Filtering the sine wave. Capacitors.
These capacitors here are used to have an oscillator. So an LC is basically like a pendulum. You had that? Did you have that in electronics?
Yeah.
So basically an L stores energy in the magnetic field, a C stores energy in the electric field. And when you have an L and a C in parallel, it basically shifts energy from the magnetic to the electric field and back. Right. And the size of the capacitors and the coil determine the oscillation frequency. It's actually 1 over square root of L times C. That's the angular frequency. Right. Yeah, so, but eventually I guess all the oscillators will be replaced by digital generation of sinusoids. Where, for instance, you have a lookup table where you store the different sinusoids, and then you go over this lookup table at different speeds to obtain different frequencies. So that's basically where technology is going. More and more of the analog components are replaced by digital components because they are easier to manufacture and more precise. Right? Here you still have to adjust the component sizes, and particularly the L is very difficult to implement in integrated circuits. So that makes them a little bit more expensive. Yeah, also the capacitors are kind of hard to implement. So when you have L's and C, it's kind of tougher to implement it in integrated circuits But if you have everything digitally, you can miniaturize it and put it into small integrated circuits. Yeah, so now we have our different frequencies from an analog oscillator or digital oscillator. And what actually happens when we do the mixing, this multiplication? So we have a carrier signal, sine of omega t times t. So this is the temporal function. T is the time. Right. Omega t is the angular frequency of your transmitter. For instance, ft would be the 480 megahertz. Right. So this is a fast oscillation over t. And then you have the local oscillator signal, sine of omega LO times t, the some angular frequency 2 pi FLO. Right? And now we multiply those two frequencies. So we have sine of omega t times sine of omega LO t. Right? So it's actually just trigonometrics, and it's easiest to see the result if you use complex exponentials and the Euler formula. So we can rewrite the sine function as the imaginary part of e to the j omega t. Are you all familiar with this Euler formula?
Yeah.
Okay. So imaginary part is simply taking this expression minus the conjugate complex expression and divided to 2j by 2j. Yeah, so when you multiply those two, we take the sine expression, the Euler formula for each sine expression, and multiply the two. So now we can see that we can multiply out this expression. So we have this term times this term plus this term times this term. So this is what we have here, right, the first two. And then we have the mixed terms. This term times the second term, we get a minus sign here. And this term times the second time, again we get the minus. So this is what we have here. Can you see it? And now you can see this is actually another sign, right? It has the same form. Here we have a complex exponential, here we have the conjugate complex exponential, here because we have the minus here in the exponent. And we have the minus sign here, that means we have expression minus conjugate complex expression, that means we have the imaginary part. And no, we have the plus, interesting. Oh yeah, the minus cancels here. So this is plus because this is minus times minus is plus. So if we have expression plus conjugate complex expression, we have the real part, and the real part is the cosine. Remember? Yeah. So that means now we have the cosine of the sum of the two frequencies plus the cosine of the difference of the two frequencies. And this is actually what we wanted to know. So now we get two new frequency components. One component is the sum, and another component is simply the difference. Right. So why does it help us? What do you think? Any idea?
I think it's now possible for us to know for which frequency we have to build our filters for filtering out our channel and then demodulating it, or to put it the other way around, which frequency we need to use for our oscillator in order to move the spectrum of the signal to the channel where we are going to use the fixed filter later.
Exactly. So for instance, take our example of 480 megahertz and our filter, which has a passband at 38 megahertz. At what frequency should we put our local oscillator? It's actually more than one possibility. do you think? We want to receive 480 megahertz. Our transmitter transmitting of 480. And we know we have a filter operating at 38 megahertz. So somehow we need to get our 480 megahertz to the 38 megahertz. So at what frequency should we put our local oscillator? FLO. Any idea?
We want 40 megahertz.
38.
48 megahertz.
No, from 480 that goes into the antenna, but our filter is on 38 megahertz. So we want to somehow shift our received frequency of 480 megahertz down to 38 megahertz. Yeah.
Then we can use an oscillator with 62 megahertz, so that the difference in the second parentheses ends up at the 48.
Right. So basically we could use either 400 for FLO, we could use 480 plus 38
Minus.
or minus. Right. So if you use plus, we have 480 plus 38. So that would be 518. Right. Good. So we could use 518, or we could use 480 minus 38.
440.
442, right? 442? Yeah. So we have the choice. Either we put it 38 megahertz below or 38 megahertz above. Both works. And by convention, most of the time the receivers have the frequency above. Right. Yeah, and that's basically the important part. So what do we do with the plus component? So, for instance, if we use the 518, right, 518. So, the oscillator is at 518. Then we have the transmitted frequency at 480. So the sum is how much? 480 plus 518. Somewhere near 1 gigahertz, right?
998.
Yeah. So what do we do with the 998 megahertz? Is there a problem?
We can use minus sign here.
Why? So basically, what we want to have is a 38 megahertz, which you already have, but then at the same time, we still have 998 megahertz, but then we don't really care, right? We have a passband at 38 megahertz, and 998 is way beyond the passband. So the sum term is there, but it doesn't harm, right? It's harmless. We don't care about it. We can just ignore it. So that's a good part here. We get mixing, we get something useful, and then we get something not useful, which we can ignore because it doesn't harm. Yeah, and here's an example how it looks like. So here we can see the first plot we can easily make with PyLab, IPython PyLab. So I used it in the Linux shell. You can just start the interactive mode, IPython minus PyLab, and then type these lines here, and you get this nice plot. Right? So it's also an example of where you can quickly test something in IPython. So this might be your carrier wave, the 480 megahertz. And then in the second plot here, you have a somewhat higher frequency. This might be your 518 megahertz here in the second plot. And then we multiply the two and plot them. Here's the multiplication, and we plot it. And this is how it looks like. And here you can see we have both the sum and the difference. Can you see where the difference is?
At 90 degrees. At 90 degrees.
Right, it's the slow change.
Yes.
Right? The slow change is the difference frequency. And then this rapid change is the sum difference. Is the sum component. Right? So this shows you how it looks like when you have both, the sum and the difference. So basically we don't care about those fast changes, all we care about is those slow changes after mixing. Yeah. So this is basically what we need to remember. We have two new frequencies, the difference frequency and the sum frequency. So the filter is tuned to the fixed difference, and by varying the oscillator frequency, different transmitter frequencies can be passed in this way, and a fixed filter is sufficient to separate all stations. And this applies to both analog and digital transmissions. So here's a little image. You can see vertically is the frequency, and then this yellow peak shows the passband of our fixed frequency, and what comes out is then passed to the demodulator. Right? So what's passed is then the desired station, and we can then demodulate it. Yeah, this is also used, for instance, for satellite broadcasts. They're usually operating in the band of 10 gigahertz, and that's too high for transmitting it over cables. So what it's done there is that in the LNB, which is right on this satellite dish, we already have a conversion down to around 1 to 2 gigahertz. Right? And this conversion is done exactly in this way. We have an oscillator, we have a mixer, and this oscillator might operate at, say, 12 gigahertz, for instance, and then it mixed down into a range where you can actually use an antenna cable. So here this antenna cable can carry 1 to 2 gigahertz. Still have a lot of attenuation, but for distributing in a house, it's still okay. Yeah, and also this 10 gigahertz is not used for terrestrial transmission because it's easily attenuated by humidity, for instance. If you have clouds or trees or walls, it's blocked. So the propagation on Earth would be not good. That's why UHF is used on the ground. So 480 megahertz, for instance, and for satellite we can use 10 gigahertz because we can always look for some spot where we have direct sight to the satellite. And you can actually sometimes notice when you have a thunderstorm in the path to the satellite, then actually transmission fails. Have you noticed? Sometimes when there's a thunderstorm cloud on the way to the satellite, then the images, the programs are interrupted. So that shows that the 10 gigahertz is kind of sensitive to water. Yeah, and also as a consequence of this mixing, for each oscillator frequency, we now have two frequencies which we can now receive. One is this intermediate frequency below the oscillator frequency, and the other is this intermediate frequency above the oscillator frequency. So in our example, when we have 518 megahertz, we can receive 480 megahertz, but we can also receive 518 plus 38. Right? So in principle, we receive 2 stations at once. So that's also not so good, and that's why receivers have a built-in filter which tries to suppress this higher frequency, right? The 518 plus 38. And cheap receivers have cheap filters which have not much attenuation, and that's why you can get interference. For instance, when you have cheap FM radios, you might be able to, near airports, to hear airplanes, pilots, right? Because they are above the FM range. And it should be attenuated, but cheap receivers don't have that much attenuation. And this attenuation is called mirror frequency suppression, and this is what you often find in data sheets of receivers. So the bigger the better. Yeah, and mixing I can also demonstrate with an audio signal. So here I'm using a little Python script to mix an audio signal from a microphone with 500 Hertz fixed frequency. So here this 500 Hertz comes from a digital oscillator, it's digitally generated. And then the mixture results in 500 plus minus the speech frequencies. Right? Or speech frequencies plus minus 500. And the downshift is actually not so noticeable, but the upshift makes it sound like a Mickey Mouse voice. So when I talk into it, I sound like a Mickey Mouse. So here it uses the Pi audio library, and this is the program, and I can open it. Let's see. So when I go to the shell. So here you can see the code that I'm using, and you can see here I'm using the Pi audio library. I'm using a block size of 5,000 samples, which also gives me some delay to avoid feedback. 2 bytes per sample, which is standard for audio, 48,000 samples per second, and I'm using a record time of 8 seconds. And actually this record time is not used here, I have an infinite loop. So here you can see it reads from the audio card, then it here converts it to short integers, and here to an array of short integers, or a list of short integers. Here I'm having my local oscillator frequency. Interesting, it's changed. Oh. So. Do you see why this is producing 500 Hertz sinusoid? Here we have a range which contains samples from 0 to chunk size. Right? So 0, 1, 2, 3 and so on. And here I divide it by the sampling rate. So after dividing this range by the sampling rate, it goes from 0 to 1 in small intervals. Right? And when I multiply it with 2 pi, which I do here in the beginning, then I have one sinusoidal oscillation, one period. Right? Then the sine, we have a sine of a sequence of numbers going from 0 to 2 pi. Right? This is one period. And when I then multiply it by 500, then I have 500 periods over this chunk size for 1 second. Well, chunk is actually less than 1 second, but that means we get a sinusoidal function for the duration of 1 block here with a frequency of 500 Hertz. Make sense? So imagine this chunk would be rate, then we would have 500 oscillations in 1 second. Yeah, and then next step here, I'm taking my samples from the sound card and just multiply it with this S. Right. And actually here this S in line 47 is also a good example for a digital oscillator. Right here we have the sine function. The sine function could be implemented, for instance, as a lookup table. And then in this way you could get a sinusoidal oscillation with just one line. Right? But just sampling at different speeds gives us different frequencies. So in this case here, this factor of 500 tells us in which speed to sample the sinusoid. Make sense? So now we multiply it here. Next line, we clip it at the maximum values of 32,000 to avoid overloading the sound card. And then we convert it back to bytes and read it back to the stream. Then we should hopefully hear something. So let me try now. This is a test. 1, 2, 3. 1, 2, 3, 4. Can you hear me? So could you hear it?
Yeah.
So maybe I can make it a little louder. This is a test. 1, 2, 3. This is a test. 1, 2, 3, 4, 5, 6, 7. Funny, huh? So this basically shifted my voice 500 Hertz down and 500 Hertz up. But the Mickey Mouse part was the upshift. Right, and this was the most noticeable one. So this shows that indeed we get this frequency shift. So that confirms our theory. Our theory is working here. Okay. Yeah, so this is actually something you can easily also try at home with your laptop. As long as you have Pi Audio installed, it should work. And if you don't, you can easily install it in a Linux terminal shell using this command, sudo apt install -pi audio. Okay, so that brings me to the next set of slides. Yeah, so we saw that we need to do this mixing. So how do we get our user information, bits of sound, video on the transmitter or the carrier wave? Right, now we know how to get the carrier wave in the receiver and separate it from neighboring channels. But we still need to know how to obtain the bits or the information. And the oldest possibility is amplitude modulation. also called AM. And AM is also what you see on cheap radios, but there it's for medium wave, because on medium wave the modulation is used is amplitude modulation. So actually AM is the modulation kind, amplitude modulation. Yeah, have you all heard about amplitude modulation? Okay, it's actually fairly easy. So in AM, the information is in the amplitude of the transmitter wave. Right? You basically have a value that you want to transmit, an analog value, for instance, from your microphone, and you have a wave of fluctuation, the value fluctuation is up and down, right? And you have positive and negative values coming from the microphone. And now what you do in amplitude modulation, you just shift this wave from the microphone above zero, and then you multiply it with a carrier wave, such it has the same fluctuation. This was actually developed by Fessenden in the beginning of the 20th century, and first experiments was transmission of voice to ships, because in this time the only wireless communications was to ships. Right? They used Morse code to transmit information to ships, from ships and to ships. And he made those experiments instead of using Morse code to transmit voice, but in the beginning the benefits were unclear, because they used telegraphy for transmitting texts. Right? They were not really interested in transmitting voice, because there was no market at the time. Radio still needed to be invented. Right? And that's often the case for inventions. New inventions need to create a market. Right? Before there is a market, there is no demand, and people don't see the benefit. So this actually created radio later, and then it became obvious what it's useful for. Yeah, and AM is also part of digital modulation modes, particularly quadrature amplitude modulation, QAM. This is used, for instance, in DVB, digital video broadcast. Yeah, and it's also used in analog color TV for the color components in parallel. So the mathematical formulation is actually quite simple. We have a signal to be transmitted, and we just assume that it's normalized, which means the magnitude is smaller than 1. And we have a carrier wave, which is sine of omega t times t, with omega t as carrier frequency. And then mathematically the amplitude modulation is simply taking 1 plus s of t. This is always positive, right? Remember, s of t magnitude is smaller 1, and that makes plus s always positive. Then times some a, depends on the power of the transmitter, and then the sine wave. Yeah, the 1 is there to make sure that it's always positive, right? That the information is in the magnitude of the wave. So here's a visualization. You have a signal, for instance, an audio signal from the microphone. Then we have a transmitter wave. And then here you can see how this audio wave is put on the transmitter wave. So we have this 1 plus s, which means we have a shifted version, and then we multiply it by the sinusoid. So the envelope now has the same form as the audio wave. Make sense? And since it's symmetric, you can see the same shape also below here. Yeah, what are the properties? Well, we can first reformulate the expression. So 1 plus s times a times sine omega tt. We can just multiply out the two parts of the sum. So the first part here is just a times sine of omega tt, and the second part is s of t times a times sine omega t. Right, and here you can see the first part is just a constant carrier wave. Right? There's no s of t in this first part. So that means this first part carries no information about the signal that we transmit. Right? So this is basically wasted energy. The second part here contains our actual information. So this is basically a mixture of the signal S with the carrier, and in addition of the pure carrier. So here we can see we have multiplication from our audio signal or the image signal, whatever, times our carrier frequency. So this is a mix again, right? And as we just saw, multiplication mix means some frequency and different frequency, right? So as a result, when we look at the frequency domain, we have the carrier at the carrier frequency, and then we have two components, carrier plus signal and carrier minus signal. Right. So, meaning we have two frequencies, carrier plus signal frequency, plus and minus short. Yeah. So how do we demodulate it in a receiver? So oh. Oh, that's better. Yeah. So the advantage, probably the main advantage of AM is that it's extremely simple to demodulate. We just need a diode, basically. So here we can see the symbol here is the diode, and in comes the intermediate frequency from our intermediate frequency filter, and this basically passes 1/2 of our waves coming from the intermediate filter. Right. And then here we have a capacitor, and this basically smoothes it so that we just keep the envelope. And remember, the envelope was just this A times 1 plus S. Right. So you can see what happens. Here is the diode curve, here's the voltage, here's the current, and you can see in one direction the current goes up, in the other direction it's minimum. So this is the equation, the diode equation. You can see it's an exponential term here, so very non-linear. So here's the voltage, and the exponent e to the u divided by this fixed term here, -1 gives you the current of the diode. Did you see this equation before? Maybe first semester electronics? Okay. So it's a very strong nonlinearity, and you can graphically represent what it's doing here. After diode, you just have the positive parts of the wave left, right? As you can see here. And after low-pass filtering with the capacitor, it smoothes out those fluctuations, and what's left is just here the envelope. And this envelope, remember, was this 1 plus S times A. So basically, this is now our speech waveform multiplied with some unknown A. And this factor A depends on the reception strength. So this is actually characteristic of AM. If you have weak reception, it becomes very, very soft, very quiet. Right? If you have strong reception, it becomes loud. Unlike FM. FM, you just get noise when you have a weak station. Here you get a soft station when it's weak. Yeah, it's very simple. And we can also do it mathematically or digitally by multiplying our received signal with a complex exponential, basically a rotating vector, at the carrier frequency, and then low pass to remove the sum frequency. And then you simply take the magnitude instead of the diode. So this can be seen here. Basically, we apply magnitude to the output of a low-pass filter of some AM signal, which I call here AM of t. So AM of t here is our 1 plus s times a times sine omega t times t. So in the receiver, I take this received signal here and multiply it with this e to the j omega t t. So this is now supplied by the receiver, this oscillator. And here I replace the AM by our expression here, 1 plus s times, and this is now our complex transmitter wave. So we just write it here as a complex exponential. Again, using Euler's formula here. So both together you can recognize as the sine function here. This is the sine omega t. And this is our local oscillator, which I now implement digitally as e to the j omega t t. Right. And then we can multiply this out and we get the sum frequency. And here we get the difference frequency. You can see here the difference in this case is 0, because carrier wave from the receiver minus carrier wave and the carrier wave from the transmitter minus carrier wave in the receiver gives 0. So e to the j0 is 1. Right? Something to the exponent 0 is always 1. So when you apply the low pass, it removes this part here. This part, this 2 omega t, is a very high frequency, and the low pass removes it. So what's left is only the 1 here. So this is what we get. So now we have 1 plus s times a to divide by 2j times minus 1, and the magnitude here is simply 1 plus s of t times a divided by 2. Make sense? So this is basically again mixing with a local oscillator in the complex domain. And you can see we don't even need a diode here. If you have it digitally, we can just use a complex exponential oscillator to do the demodulation using the magnitude here instead of a diode. Remember, the magnitude is also the envelope of our carrier wave. Yeah, and here is also scaled as in the diode case. So we have this A over 2, which depends on the reception strength. And we still have this DC offset by 1. Yeah, and in a software implementation, we can actually avoid complex arithmetic by reformulating it. So we can implement it by two-carrier oscillation, the cosine and sine oscillator, corresponding to the real and imaginary part of the complex exponential here. So you can see we can reformulate this into cosine plus j sine. Then we have those two terms here. So basically we have two parallel mixers, now each real-valued oscillators, but the oscillator is shifted by 90 degrees. One is sine, the other is cosine. Right. Yeah, and when we take the magnitude, here we can see it's still complex, but the magnitude of real and imaginary part is square root of real part squared plus imaginary part squared. Remember? So A plus JB magnitude is square root of a squared plus b squared. Can be seen as a triangle. Right? So rectangular triangle. Yeah, and this last line here is basically all real valued arithmetic. So we don't need to use complex arithmetic for implementation. Right. So here we just need to have the received signal am of t multiplied by a cosine oscillator wave and by a sine oscillator wave. Apply the low pass twice and then take do the sum and then take the square root. Yeah, what is the bandwidth of AM? That's important for planning how many stations you get on the band, for instance, medium wave. So we already saw we got carrier wave frequency and then carrier plus minus signal frequency, right? So what's the bandwidth? What do you think? From the highest to the lowest?
It's twice bandwidth of the carrier, of the signal frequency.
Yeah, right. So the signal that we modulate, it depends on the signal that we modulate on. For instance, the audio signal or the video signal. And what we get here is twice the bandwidth. Right? We have this factor of 2 because we have plus and we have minus. Yeah. So it's also easy to see when we turn our signal to be modulated, the useful signal S of t, into a sum of sine signals with the help of the Fourier transform. And this applies to sound as well as to images. It should be spatial frequency. Spatial frequencies. Yeah, and to see the bandwidth, we can just take the highest frequency that appears in the mix. And that might be our omega s. And then we can see here in the mix we get carrier minus this signal and carrier plus. And right. So here we have the modulation, 1 plus s times a times sine. And here we can see the carrier, and here we can see the sideband, the so-called sidebands, which comes from the multiplication of the carrier with the signal. And here we get the sum and the difference. So this is then the resulting spectrum. Here's the carrier wave, here we have the frequency axis, here's the so-called upper sideband, where we have the sum, and here's the so-called lower sideband, where we have the difference. So the total bandwidth is 2 omega s. It should be the carrier. Yeah, and the demodulation using a diode can be also analyzed using its nonlinear shape. Right? When we look at what happens when we apply the diode, we can describe the function of the diode as a Taylor series. Right? We saw we have e to the u divided by some constant, minus 1. And here you can see e to the x can be written as the sum, an infinite sum of x to the nth power divided by n faculty. Right? And this, among others, contains a quadratic term, x squared. Right? When we have n equals 2, then we have the x square in it. So we have a lot of stuff in it, but among others, we have the square. And if we have the square, and x is now the sum of the carrier and the two sidebands, then when we square a sum, this is what happens. We have the individual terms as square functions, and we have a mixing term, 2ab. Yeah. So X here X contains the sum of the carrier plus and the two sidebands. So here we get the multiplication again. So in the AM wave we have those frequencies, carrier, upper sideband, lower sideband, and for the multiplication we have the sum and differences. Right. You can see the first term is the sum of all those frequencies, so here this plus this. Second term is carrier plus this here. And so on. So we have all combinations. So now the interesting parts have to be filtered out using a low pass filter, and you can see the lowest frequencies contain the part where you have omega t minus omega t, and what's left is the omega s, the signal frequency. Right. Those high frequency components, where you have the sums, they will be blocked by our low pass filter. So basically, using a diode for demodulation, mathematically again, is mixing the amplitude modulated signal with its own carrier. Right? The carrier is already mixed, and when you apply the diode, you basically square what's coming in, and that leads to this mixing. And in the mix, among other frequencies, is this original frequency omega s. So in principle, diode demodulation is also mixing, but without a local oscillator, but using the carrier frequency supplied by the transmitter. And that's what makes it so cheap, right? The diode doesn't need a local oscillator because it gets, for nothing, it gets the carrier. But that also makes the transmission expensive because they have to transmit the carrier, which consumes a lot of power, but doesn't really give any additional benefit. So the only reason to use this carrier is to make the receivers cheap. Yeah, so mixing with the carrier shifts the signal back to the base frequency of the signal to modulate, and the carrier at the amplitude modulation has no own information. It is only needed for simple mixing in the receiver using the diode. And if we were able to generate this frequency in the receiver, we would be able to do without this carrier. So if we have a precise local oscillator, then we wouldn't need the carrier. And omission of the carrier would have several advantages actually. It saves transmission power, which can be a lot. And it also reduces the interference potential from neighboring stations. Right? Often the carrier is the strongest signal in the neighboring station, and that can interfere. And omission of the carrier in the transmitter is easily possible by omitting the DC offset, the term 1, in the modulation. And this simply results in sine of omega s times sine of omega t times a. Good. So it's actually quite simple in the transmitter. And this way we only get the two sidebands with the actual useful information. In the receiver we can demodulate the signal by multiplying with the locally generated carrier frequency, or the local oscillator. Yeah, so here the local oscillator. Yeah, but the frequency must be very accurate, otherwise there are frequency shift in the demodulated signal. Right? As we just saw from my little demo, Right? Just shifting by 500 Hertz makes my voice sound really funny. So if we have the same in the demodulation and our local oscillator is just 500 Hertz off, it basically makes the demodulation useless or unusable. Right? So this oscillator has to be very precise, down to 1 Hertz maybe. So that makes it expensive. Yeah, so here I have a little Python example for modulation. So in this case, this is for our little demo where we want to transmit bits. Right, so we need the library PyAudio and my library sound.py. So sound.py is in the Moodle. Right? If you look in Moodle for this lecture, you will find sound.py, and this makes reading in sound and playing out sound easier because it contains all the access to the sound card. Okay. So now let's assume that we have a carrier frequency of 1000 oscillations or hertz and a sampling rate of 32,000 samples per second, or 32 kilohertz. So first we can see how the 1 kilohertz sound tone sounds like. So in order to generate its sample values, we can write this little IPython script here. So here the same principle. I'm using this sine function. I have 2 pi divided by the sampling frequency. Then I have this range, which gives me the sample numbers. And then I multiply it with the 1000, which is the number of periods per second. Right. And let's see. I can try it here in my little terminal shell. IPython -pylab. So here you can now see that we are in interactive mode. Can you all see it? Can you all recognize it? So this colorful prompt tells me that we are now in interactive mode of IPython. So that I can just copy and paste this. Hopefully it works. Copy. Paste. And now sound. So now I'm using my library here. Copy. Yeah, so this was a 2-second 1 kilohertz tone. This is how 1 kilohertz sounds like. And we want to take a 2 hertz signal to modulate it. So here we have the tone, which is just 2 hertz. Copy, paste. So this does not need to be normalized because it doesn't exceed 1 anyway. So I can actually plot tone. So you can see how it sounds like. This is my 2 hertz tone for 2 seconds. And you can see indeed we have 4 periods. Means 2 per 1 second, 2 per second. So indeed a 2 hertz tone between amplitude between -1 and 1. Yeah, now we can do the amplitude modulation. So remember, here Träger was the 1 kilohertz tone, and here we do now the multiplication, the shifting and multiplication. AM and now plot AM. So this is how it looks like. Does this look reasonable? Why is it all blue? What do you think? Shouldn't it be an oscillation? Yeah?
I think it is an oscillation, but because the frequency or wavelength is so narrow, we can't distinguish the individual lines in the screen, so there's just a blue surface.
So how can we check?
Put it in.
Exactly. Does it make sense to everybody? So there are so many oscillations that they look like one blue color. So fortunately here in IPython we have this zoom tool, so we can just take one piece here, zoom in, and here we can now actually see the individual oscillations. So I can zoom in a little bit more. See, it was really like sinusoidal oscillations. Yeah, so this is how you can check. You just zoom in. Yeah, so this is what we got. And now we can also listen to it using the sound command. Copy. Good, here it goes up and down, so it becomes softer and stronger. So that's actually the characteristic of amplitude modulation. The information is in the up and down of the tone. Yeah. So this is basically our 2 Hz tone modulated on this 1 kHz carrier. Yeah, and in old times we would have an oscilloscope, or actually also newer times when we want to analyze transmissions over the antenna, we would have oscilloscopes, and then on their screen you would see those images. Right? So you would have the x-axis would be the time, and the y-axis would be the envelope, and this is then the typical image you would see. So there you could check if everything is okay. Yeah, right, so here I'm zooming in. Here you can see part of the carrier wave. And now we can also calculate the Fourier transform using the command FFT, right, to verify that we indeed have the carrier and the 2 sidebands, the upper and lower sideband. Right, so what we do here is these commands and give them a different font. So how does it work? Jeez. Okay, whatever. Copy. Yeah, so this is what we get. So we have now an FFT of length 64,000, and I just plotted half of it. Yeah. So here you can see I'm using the first half because we saw we have this symmetry, right? Because the upper and the lower, and we're not interested in this upper mirrored version. So I only plotted the lower half. Right, and remember then this index here refers to the Nyquist frequency. Right? So this is Nyquist. So what's the Nyquist in this case? What frequency in Hertz? Remember the sampling frequency?
Divided by 2. The sampling frequency divided by 2.
Yeah, remember the sampling frequency?
With the practical that we
yeah, 32 kilohertz. Yeah. So 32 kilohertz, half of it is 16 kilohertz. So here would be 16 kilohertz. Right? And that means here this peak here should be at 1 kilohertz. Because we have a 1 kilohertz carrier wave. So where do we see the two sidebands? Do you see the two sidebands, the upper and lower sideband? I don't see it, right? Why don't we see the two sidebands?
Yeah, it's once again because the scale is set to zoomed out, because we only got a signal frequency of 2 Hertz, which is very small compared to 3 kilohertz that we can see on the scale.
Right. So we expect the upper sideband at frequency 1000 plus signal frequency. So signal frequency was 2 Hertz, so 1002. And the lower one at 1000 minus 2, so 998. Right. And that's so close here that we don't see it. So again, the same effect as the blue color for the carrier wave. So again, we have to zoom in to see them. So again, here, fortunately, we have the zoom tool, and I can move in closely. So you can see 1900, 2100, still not much to see. Oh, no sidebands. So indeed, there are no sidebands. Interesting. What did we actually plot? We plotted the Träger. So we didn't plot the AM. Right? So this is actually correct. So now we can do the same with the amplitude modulated version. Yeah, so here I calculated which index we expect the carrier. So 1 kilohertz should be at index value 2000. So now try the AM version. So it looks the same. Yeah, so indeed here, can you see those little numbers on the right hand side? Yeah. They actually give the position of the mouse pointer. And this can be used to verify where the position of this carrier is. So here I put the mouse over the carrier, and the X value should be 2000. Right? And X you can see 1995. Yeah, I cannot point so precise. So this is about 2000. And now we can zoom in. And now we should see the sidebands. Yeah, here are the sidebands. And you can see here the carrier is precisely at 2000, and here the sidebands 1996, and here 2004. So here 2000 was twice the frequency, so that fits. So this should be 998, and this should be 1002 Hertz. Make sense? So now we indeed see those two sidebands. So that works out nicely. And you can see the picture. Yeah, so here 2 Hertz is 4 on the x-axis, so the sidebands appear at distances of plus minus 4, which is exactly what we just saw. Right. And here we can see it again, zoomed in, and they appear indeed as at this distance. Yeah, makes sense so far? Okay, yeah, I guess time's up. So thanks for the attention and have a nice rest of the day.